Okay, I think we can start now. So, hello everyone. Welcome again to the PowerSys user conference. So we are very happy to have you here. And today I'm very glad to welcome two speakers for this first customer presentation. So Shafik Nateg and Stefan Kenzelman from ABB. So they will present about efficiency, loss, and system calculation of railway and e-mobility traction motors in JMAG. So Shafik was born in 1994. He received a PhD degree in electric power engineering from KTH Royal Institute of Technology in Stockholm, Sweden in 2013. He was a visiting scholar with the University of Illinois at Urbana-Champaign in the US from 2012 to 2013. And then from 2013 to 2015, he was a lead designer of permanent magnet machines for marine segments with Rolls-Royce in Norway. Then he continued his career as designer of traction motors for railway application with Bombardier in Västerås, Sweden. From 2015 to 2018, so this was from 2015 to 2018, sorry. Then he was guest researchers with KTH in Stockholm. He's currently an R&D senior engineer and also a project leader with the traction department for ABB in Västerås in Sweden. And he also holds a position as an adjunct associate professor with Chalmers University in Gothenburg, Sweden. He was a technical track co-chair at IEMDC 2019 in San Diego and ICEM 2020 in Gothenburg, Sweden. His research interests include different aspects of electromagnetic, thermal, and insulation design of traction motor in marine, aerospace, railway, and e-mobility application. So our second speaker is Stefan Kenzelman from ABB in Switzerland. Stefan was born in Switzerland in 1982. He received a master's and PhD degrees in 2007 and 2012, respectively, from the École Polytechnique Fédérale de Lausanne in Switzerland. In 2013, he joined the traction division of ABB Switzerland as an expert for motor controls and other motor-related topics. In his current role, he is responsible for the software development for automotive drives. His research interests include single-phase control method, multi-level converter control, DC power transmission, induction, and permanent magnet machines, functional safety, and software processes. He has authored and co-authored several publications on power electronics and application. So welcome Shafik and Stefan. Thank you for accepting to present your work today with us. So Shafik, I think you can share your screen now and start your presentation.
Thank you very much, Corentin. So, okay, I guess you see now my screen.
Yes, we can see your screen.
Yes. So as mentioned by Corentin, I together with my colleague, Stefan Kenselman, will present our experience with JMAG on efficiency loss and system calculation in both rail and e-mobility traction motors. So this part, of course, was presented by Corentin very well, and then I go then directly to the outline. So since both me and also Stefan are coming from actually R&D teams in AB business unit, so we are pretty close to the market. We would like to start our presentation with the market, but it will be quite technical market, I would say, presentation, because that way we are going to explain how requirements in the market will influence the requirements on the tools in different applications. In this case, for today, we focus on railway and e-mobility. If you haven't had the chance to see the abstract of the presentation in the website, conference website, you can also find it in this presentation. And then following our introduction on the market, we will review the design process that we have today in ABB step by step, and then we will tell you how different modules and function in JMAG from JMAG Express to Designer and RT are contributing our today design process and detailed calculation. And then my colleague Stefan will present the system calculation aspect of JMAC. This is actually the core part of this presentation. Whatever I explained before that is basically providing the input to this system calculation that at the end will be presented by Stefan. So here is the abstract, but let's see what is the difference between rail and e-mobility and how at the end this influences the need for the tool. So this is an slide, quite old one, with focus on ABB, basically products or old like company, which later on were purchased by ABB. As you can see, railway market or electrification of railway has a quite long history. You can say the same with e-mobility, the first electric cars. But the difference between railway market and e-mobility is that this development has been always continuous until today. However, electrification for vehicle has started quite a long time ago, maybe in the same century, but then it was totally stopped. And now we see a lot of activities, I would say, during the last 10 years. So, and looking at the market, how the market is going to grow until from 2018, for example, to 2025, we see in rail quite a stable, a slow growing market with the average of compound annual growth rate of something like 4 or 5%. Most of this growth is going to be seen in Asia and then Europe, North America, at the end, the smallest one goes also to Middle East, maybe because of the lower price of the gas there and the tendency of the people to use more vehicles. Anyway, so the conclusion basically here is that on the market, there is not a huge growth or blow up as we see in the e-mobility. But putting the market on the side, if we look at like different segment of railway and how during the last years the solution has been standardized, it gets actually quite interesting. We are able to basically classify railway in 5 segments, starting from the smaller ones, which are like light rail vehicle, for example, monorail. And then it goes to metro EMUs, which are mostly used between the cities to move people between the cities. And then we have high-speed trains and locomotives. Of course, locomotives need quite high level of the effort during acceleration and also at their own higher level of the speed. That's why they need, you have the highest requirements on locomotors. And then you have the high speed trains, which are also, they need also quite high level of the torque at low speed and also, of course, at high speed, mainly because to limit the maximum speed of the motor, we need to use pretty low gear ratios. And lower gear ratios means that you need more torque. Then it will go, of course, to the EMUs and metros and LRVs needs the lowest level of the torque in comparison to, of course, high-speed trains and locos. This is more like a generalized picture. There are always exceptions. Okay, and then let's see how the basically different segment of the market has resulted in kind of a standard products at the end of the day, not on the electromagnetic side, but also on the cooling side. So we will start again with light rail vehicle. The most topologies being used in this part of the market is copper rotor and also aluminum rotor induction machines. When it comes to cooling system, we have basically two kinds of open self-ventilated motor and also here I wrote it closed self-ventilated motor, but the fact is that they are semi-closed self-ventilated motors. And for example, when it comes to monorails being used inside the city or intercity, like monorail, then you have low floor monorails, which are pretty much subject to high level of the dirt. That's why closed self-ventilated motor are mostly used there. And when you have closed self-ventilated motor, that means you don't have the active cooling of the rotor. That means you need less losses in the rotor. That's why the copper rotor is the dominating topology here. When we look at like suburban, for example, trams with high floor kind of topologies, then they are less subject to the dirt. You can use open self-ventilated where you have cooling in both the stator and the rotor. And having cooling in the rotor means that you can produce more losses in the rotor. That's why you are able to use more low-cost solution, for example, aluminum rotor induction motors. When it comes to the metro, other requirements comes in. In metros, it's always about the cost. That's why they normally run 4 motors in parallel with one converter, and then influence of running parallel motors with one converter comes in. We know that having higher level of the rotor resistance will actually reduce the influence of or Lloyd difference between the motor when you have this high number of motors in parallel. And also because of the cost aspect, then aluminum rotor induction motor is like the dominating basically topology here. With EMUs, everything is about the efficiency is quite important there. That's why copper rotor induction motor, or in some cases also PM motors, are being used. And also the need for having constant cooling, no matter of the speed of the train, has resulted in using mostly force ventilated motor. That means you have the separate cooling on the roof of the train most of the time, providing the motor with the needed cooling. So the cooling is not dependent on the speed of the motor. And then you have high speeds and high-speed trains and also locomotive that, as I said, the requirement on the torque is quite high. They normally end up in quite big motors, and because of the size of the rotor and also some aspects on the production, copper rotors are normally preferred for this solution. For high-speed motors, also due to the efficiency. High-speed trains also due to the efficiency, copper rotor is preferred. But for look, it's mostly production aspect. So as you can see, during the last like 20, 30, 40 years, uh, almost all the segments has converged into kind of a standard solutions, both in electromagnetic design, but also the cooling for rail. This is not just about these two aspects, but also other detail. For example, the insulation design has become very much a standard. If you look at different OEMs, you see almost the same insulation concept. Maybe the brand of the material they use, or also small changes in the concept of the material can be seen. But in general, it's the same electromagnetic, the same cooling, and almost the same insulation system. Now, let's see how it is in e-mobility. In our department at ABB, we focus on heavy hybrid vehicles or electric vehicles. So we don't work so much on passenger cars. So whatever I'm presenting here is mostly on heavy electric or hybrid vehicles. I showed you the graph, how the growth is in rail, but now you see how the growth is in e-mobility, and you see totally different picture here. The growth rate is going to be pretty high with quite big slope until 2030, and it's gonna be a little bit maybe a slowdown there, but they're still growing. And that's all in all the market, no matter if it is commercial vehicle, light, medium, or heavy commercial vehicle, or it's, for example, off-road, for example, mining vehicles. They are all gonna grow. The same picture we see here from Bloomberg. You see also some contribution of the country. This also includes the passenger cars. The same trend, quite a steep increase until 2030, and then slowing down a little bit, but still continue growing until 2040 or afterwards. But also, if we just now focus on heavy hybrid or electric vehicle, we see also in this market quite big changes in terms of the design requirements for different segments of this market. So as you can see, when it comes to the max torque and also power, mining equipment and also construction equipments are like the most demanding ones. But when it comes to the lifetime expectancy, then buses, electric buses, and also light, medium, and heavy commercial vehicles have the highest requirements. So you see, we have in this market, however, we are now focusing on just part of the market, which is going to commercial vehicles and also heavy, basically, vehicles. Still, the requirement is changing quite a lot here. And that's basically how I summarize here. We have railway market, pretty standard electromagnetic design, cooling design, and insulation. And then we have e-mobility that is still some people talk about axial flux, radial flux, and even the main topology is not yet decided. So I told you our focus is in heavy vehicles, but we can always learn from also passenger cars. And this is basically this picture, this summary shows how different is like the solution for different OEMs even today. Some OEMs are using synchronous motors, some of them like a wound field motor, some of them are using induction, some permanent magnet, some of them are using rare earth, some of them are using freight, and they are coming up with non-rare earth solution. So all this basically shows here, I have summarized in this slide that I like it very much basically, and the fact that shows railway during the last decade, especially after the time of DC motor, has come to AC solution, induction, and for different segments, solution has converged basically to very specific topologies and also even designs and also detailed designs for each segment. And this is expected to continue from now until 2025 or 2030. However, what we have seen in e-mobility so far has been that the solutions are being expanded. And, and this is until now. My guess here, this is just a guess from my side, and this is based on some signs that we see, is that these expanded solutions are going to converge during the next 5 to 10 years, actually. And then after that, considering a lot of developments has happened in e-mobility, the question is that how this development, how this lower cost, how this new design, new ways of production will influence the other segments of electrification, for example, in rail and marine. We don't know that yet, but we can guess something that there will be a lot of overlap in future. So, and this is basically how, from this slide, we can see how the requirements are in the tools, basically. When it comes to the railway, the design is pretty standard, not so much optimization. You basically need to mostly scale the design for the requirement that you have for that specific customer or OEM. And then many of the OEMs have developed their own internal tools during the last decade that is working very well, has been calibrated very well. And the main usage of advanced tool, for example, JMAG, comes to very detailed calculation. When it comes to calculating leakage inductances, when it comes to calculating losses and efficiencies, that's where you need the advanced tools, for example, JMAG, or what we call it as external tools. However, if you look at in e-mobility as well as the need that you have in rail on doing detailed calculation, for example, losses, inductances, and the other motor parameters, but also the main topology of the motor is not yet converged, or we don't have any standard solution. That means you need also tool that can support you and can contribute in topology selection and also design optimization. And that's where also JMAG comes in when it comes to the e-mobility. So here is basically our design process at ABB. I'm just talking about e-mobility. As you know, ABB is quite big company with many segments working on different applications. This is basically what we have in e-mobility. Of course, we always start with topology selection, and that's where JMAG Express comes in. Then we do initial dimensioning of the motor and a little bit of optimization. When it comes to optimization, I'm talking about, for example, the main points of the design, which are, for example, the number of turns, and the parameter that mainly changes the inductance of the motor, which are pretty important for system calculation. When we are there, we are ready to send the motor model to our system calculation colleagues, which is in this case Estefan, who is also here and will present how he does his own calculation. And then we will continue with doing detailed calculations. And that's where we continue using JMAG Designer. And when it comes to detailed calculation, I'm talking about very specific, like detailed parameters in the rotor, diameters of that corner of the barrier, the thicknesses, and the other detail parameter that will not maybe so much influence the system calculation on the system level. So for calculation system level, mostly we use, of course, RT, and we have successfully used it in the software. Hopefully, we can also use it in near future in the hardware as well. We will see how it will go. So now that I presented basically the design process that we have, I am going to give you just some example of the calculations that we have done in JMAG. Some parts are already published, so I have put also the reference. So for more detailed presentation or papers, you can look at, for example, you can see the result of the IECON conference that will happen within a few weeks. And we have a paper there together with the JMAC, sorry, PowerSys. And then, but anyway, I will review what we have done, and then I will stop my presentation. I will try to end it by the JMAC RT, and then it will go to Estefan. So let's see when it comes to detail loss and efficiency calculation. What matters for us is that the tool that we are using should be able to cover different topologies that we are using today. I told you in Emobility it's hard to say which topology is dominating. This comes to the rotor, to the stator, to the winding, to the insulation, everything. So one important factor for us is, for example, when it comes to efficiency and loss calculation, is AC losses. And we have products with form winding, with random winding, and we are also considering the possibility of using semi-automized or fully automized, for example, hairpin winding. Uh, so that means our tool should be able to model AC effects in all this winding configuration. And the AC effect is contribution of different components of the AC effect is not the same in different winding configurations. So that's why we need to have kind of generic model and also kind of automized process to do the calculation. As I told you, we have in our design portfolio, we always look at random wound, form wound, and also in some cases also hairpin in the case of like checking the possibility of using that. This is basically this slide is partly from the presentation that we will have soon together with PowerSIF and University of Verona in Singapore in IECON conference, and it's on comparing the losses, AC losses, basically in hairpin and also random winding. So what matters here is that all the phenomena, we know we have different sources of AC losses in the winding. Part of the AC losses are coming from the time varying magnetic field, basically produced by the permanent magnet rotor, and mostly influences the slot, the area close to the slot opening, but also we have also, due to the fluxes in the teeth, also we will get some leakage fluxes inside the slot, even on the bottom part of the slot, that produce some losses. So for this kind of calculation, basically we use 2D time domain calculation, and in the whole process we use the JMAC modules. I will show you in the next slides. The same we have done for the random wound, and of course, due to the smaller cross section of the random winding, results in less contribution of AC losses. But anyway, we need to always calculate it, and because in different speed range, also we know it has different influences on the efficiency of the motor, both for random and also hairpin winding. The method of calculation between hairpin and form winding is almost the same, basically. So we don't see so much differences. The other source of the losses that we need to calculate quite accurately is, of course, the iron losses. When it comes to iron losses, we have done a lot of studies thanks to JMAG, both in separating hysteresis and eddy current losses in both stator and rotor lamination, but also studying influence of manufacturing process on the iron losses. That's pretty important. Of course, that's pretty much dependent on the material data that we have, the areas closer to the punching edges, the area that are a little bit far from that. And JMAC provides that possibility actually to do this kind of detailed calculation. I was hoping to actually present a paper on that as well very soon. We will see how it will go with our time plan. And also, of course, all this calculation has been done in 2D time domain. Another very interesting calculation that you can do, JMAC, thanks to the very wide choices that you have in the circuit module, is to also study the influence of the PWM on iron losses, but also on AC, copper AC losses. We have done that as well. And it is quite actually a straightforward to do. Of course, the calculation time is quite long. You need many steps to take into account all the time harmonics, but still it is very much possible, and we have done it successfully together with Stefan and another PhD student that recently worked on it, Grazia Berardi, who is also the co-author of the papers that I mentioned. Another calculation that we do is eddy current loss in the magnet, also including the time harmonics, and also with mapping the flux in the air gap. Basically, that you can map basically that flux. You can calculate that flux in 2D, and then you can consider the boundary condition for 3D calculation, where you can include also the magnet segmentation. That's also a kind of exercise that we do quite frequently. So to do basically this kind of calculation, we have kind of automated the whole process. First, we start with the speed priority for initial estimation of the efficiency and getting the efficiency map. And of course, the benefit of this speed priority for us is the calculation time and the time that you need for the model implementation, because you don't need to model all the conductors. But the cons, from my point of view, is that AC losses cannot be considered at least accurately. I heard there are some functions now that you can use it. I haven't tried it myself, but the module we are using so far, we haven't included the AC losses of the copper there. If you have more questions about this new module, I haven't used it, but maybe Eve can answer your question. But that's what I have read myself. And then this is a typo here. It's accuracy priority. And then in the accuracy priority calculation, that of course takes longer time. We need to model all the conductors one by one. This is a model of the hairpin motor that we have studied. And then we can do all the detailed calculation based on the output that we had from the speed priority and finding the optimal operating point considering the control. Of course, the controls cannot be very optimized, but it's good enough for the kind of calculation that we do. This is also a study that we did using JMAG, comparing random ones and also hairpin, comparing the AC losses, copper losses in the SP train. This figure is showing basically the result at full load. Of course, when it comes to the lower level of the load, let's say 25% or 50%, then when you go to the higher speed, the random winding losses will be lower actually than the hairpin. And this is the result on the efficiency again, and that's again at full load, not at lower level of the load. Maybe at 25% of the load, you will see that the efficiency of the random won't jump a little bit over the hairpin. So having that, so that's basically the loss calculation that we do. So we include basically all the loss sources from eddy current losses in the magnet, iron loss in the lamination, separating hysteresis and eddy current losses, taking into account influence of the manufacturing, studying the influence of the PWM and time harmonics on the losses. But that's on the last part. But also we need to also deliver the motor model as well as the loss model to our system calculation guys, so they are able to do the calculation and to consider motor model as a part of their system. And for that, we basically use fully optimized JMAG RT module, which is pretty easy to use. And here I have put a picture of the setting and also kind of result that we provide. Mostly provide the data to Stefan in D and Q, but this is just an example. The other good benefit of RT that we haven't yet used and we hope to be used in near future is to use it on the hardware, and we think this can simplify a lot of the processes. So thank you very much. Here I hand over to Stefan, and I will stay in the call. So if there is any question, I try to as much as possible answer. Thank you very much.
Well, thank you, Shafiq, for the introduction and the very interesting slides. So I'm coming more from the application side, and I will show how we use the data provided by JMAG for additional calculation. So if you go to the next slide. So within our workflow, we're using two tools, which we developed in ABB in my unit. That is this BEC tool, Best Efficiency Calculation tool, and the BSI tool. So they work closely together, exchange data, and are streamlined to work in a fast way. So initially, we take the data provided by JMAG, so that is the fundamental losses and the flux lookup tables. And where we have the fundamental losses for iron, copper, and magnets. So to speed up the calculation process, we decided to go for a mixed approach. So on one hand, we have this FEM simulation by JMAG, and then we have the post-processing in VSI2 and BEC2. And so in a first step, we do a system optimization. Excuse me for the short disruption. So we use the BEC tool to derive the optimal operation point for the system. So that is machine. Just a second, sorry.
Okay, I think Stefan
So
will be back.
This is the result of COVID-19. Yeah. Maybe I'm working at home.
This is something normal, I think.
Yes.
No problem, Stefan. You can
new
take your
normal.
time.
Yeah.
We don't hear you, Stefan, I think.
So we determine the operation points, which is voltage, currents, frequency, and also like different pulse patterns. And then with the VSI tool, we calculate the switching losses and the harmonic content of that specific pulse pattern. So we're not only using PWM, but also OPP, which are optimized pulse patterns. And then we take the data back into BEC tool, and we do include the harmonic losses on the motor with that given harmonic content of the voltage waveforms. In the end, we're able to derive all the system data, which is efficiency, all the losses. And this data we not only use to have an estimate on our efficiency, but we also use it to implement it into our software, where we drive our system in the most optimal way. So if you go to the next slide, the next slide illustrates the process. So we started from the sinus losses and the lookup tables provided by JMAG. And then with the BEC tool, we do a system optimization, calculate MTPA for PM machines, MTPL, the loss optimized operation. And then we give that information to the VSI tool, where we determine the converter losses, determine the different switching patterns, the harmonic content of these switching patterns, and then we go back again to the back tool, which then will calculate motor harmonics and all the other related the system losses. And you can actually also see each contribution, each element that contributes to the system losses. If you go to the next slide, we can further use this data to evaluate, for example, the lifetime of the drive on a given track. So we can again take the data from the back tool to derive the operation points of the electrical operation points, that is voltage, current, cos phi, and frequency, and the pulse pattern. And for the given track, we feed this information to the VSI tool, which then calculates the temperature evolution of the semiconductors. If you go to the next slide, again, we will illustrate that a bit more. So on the left, we have the track data. Then we use the data provided by Vectool to give us information of the electrical quantities, which then will be calculated inside the VSI tool, and all the temperature gradients, the temperature evolution of the semiconductor will be evaluated to give us the expected lifetime of the drive. So just to sum up, for us, JMAG greatly helped us to facilitate the interface between what Shafiq is doing by designing the motor and what we are doing using that motor data to derive the optimal system efficiency and this optimal system operation. And that was very important to us because customer requests were very, very dynamic. So basically, in a week's time, we had to evaluate new designs. We had to make calculations of efficiency maps, and that wouldn't have been possible if we hadn't had such an easy interface between the two of us.
Yes, and also maybe one thing I can add here, Stefan, is that the fact is that we discussed about this initial optimization and then detailed optimization. This process, and also, for example, contribution of the time harmonic losses and also fundamental losses between different design has resulted in totally different designs at the end than what we had initially. This happened several times. So it was more for both calculation, but also this feedback that we had from you based on the calculation that you did very much at the end influenced also the final design of the motor as well.
Yeah. Well, I am through with my slides. Can I have a look at the questions maybe?
I think Corentin has all the
yes,
questions, right?
Sorry, yes, we have some questions. So thank you very much, Shafiq and Stefan, for your great presentation. So we have some time to go through the question. Just want to remind all the attendees that they can ask all the question they want through the chat panel or the question and answer panel of Zoom. You can also ask question on the Wova platform. So let's go and go through some of them. So the first question we have for Shafiq is how do you calculate AC losses in random windings when winding positions are not predetermined? Sorry.
Yeah, we consider that basically. What do you mean? If the winding configuration is not determined, then we are not able to do the calculation. So winding configuration is one important input to our calculation, and we start doing this detailed AC loss calculation, detailed kind of calculation, providing the map I'm sending to Stefan when at least the initial design is finalized. And one of the most important initial design parameter, as I mentioned, is the number of turns, winding configuration. That will influence everything in the motor, right? From voltage to current to inductance and everything. Of course, as I mentioned, also this has changed several times because this link was not maybe so convenient before applying JMAG, so we didn't have so much of this link. The fact we had some link, but it was not this optimized and this friendly used before. So it was a little bit separated. But as I told you, I mean, during this process, a lot of this winding configuration, the number of conductors, the size of the conductors has been changed based on the feedback that we had from Stefan. But the fact is that not having the winding configuration, it will be actually quite hard to do detailed loss calculation. You can do some based on like what is called equivalent number of turns. Maybe you can do some calculation, but you cannot do AC calculation.
Okay, thank you. Second question. What are the engine's power, torque, and voltage ranges of the motor you design? I'm not sure if you can answer to that.
Yeah, it's up to 1 kV for Emobility.
Okay.
Yeah, it can be
Okay.
lower, it can be higher in some cases, but something I'm talking about DC link of
Yeah.
1 kV in the range of 1.
Okay, thank you.
Stefan,
Yeah.
we may add something. Maybe I'm wrong. You know more about the system.
Yeah, I mean, the voltage, there was always a question. And I mean, we're speaking here of permanent magnet motors. So there also the functional safety aspect kicks in. And that means we have to consider the back EMF in the safety design of the drive. So yeah, I mean the ranges we're speaking of are like below 1 kV for the DC link voltage at least. Yeah.
Yes. But that doesn't mean, because we have also some advanced functions on our converter. But when it comes to, for example, design of the motor and also the back EMF, we are able to, of course, apply we can design for higher value that will, of course, improve the efficiency and influence the motor performance. But on the DC link, I think we are, as you mentioned, Stefan, we are, I think, limited in this range actually.
Okay, thank you for your answers. Next question. Have you considered both induction motors and permanent magnet motors?
For which calculation?
Not sure about the question, but in general.
For losses, yes. For losses, yes. We have used both of them pretty much, but for RT, it has been mostly permanent magnet motor.
Okay.
When it comes to, of course, express, then you have all the options on the table.
Yes. And very nice question is, what's your opinion about the JMAG iron loss calculation accuracy?
If we are talking about the fundamental losses, of course, big part of the iron loss calculation comes to the production. So JMAG will provide you with enough data to analyze the input that you have. But if you are in very early stage, you haven't made so many prototypes. I mean, one good thing about companies like ABB is that we have access to a lot of measurements, previous measurements. So we have studied the influence of the production and this kind of problem quite a lot during the last decades, I would say. So my comment here is that if you have the right input, JMAG gives you the best results. So right input on the production, right input on the material data. Then you get pretty advanced and pretty good and high accuracy in JMAG for sure. No doubt about it.
Okay, thank you. So it seems we have covered all the questions so far. If there is one last time question, please ask it now.
So the OPP, there's a one question. What's OPP in the slides? OPP means
Yes, sir.
optimized pulse patterns. So it's like pre-calculated pulse patterns, which are reducing the switching losses without compromising the system harmonic content, basically. It's an optimized, offline optimized pulse patterns.
Thank you, Stefan.
I think all that we went through. I was wondering if Eve, do you have any question? Because normally when you have question about JMAG, you ask me, or so we cannot hear you.
We cannot hear you, Eve.
Sorry, can you hear me?
Yes.
Yeah, so I just posted one question, but I don't know why you can see it. I have just one question. Maybe do you plan to go for 3D calculations, or
we have done it already?
Oh, okay.
For when it comes to eddy current losses in the magnet, we have done much 3D calculation. that was more an investigation. Of course, we haven't used it for like efficiency map, like what we do 3D, because it will be very time consuming. Yes. But when it comes to like detailed study on different parameter, for example, one of them was magnetic influence of magnet segmentation on eddy current loss in the magnet, or magnet influence of the magnet segmentation, for example, on the PWM losses time harmonic. Yes, we have done 3D calculation. But except from that, we haven't done so much 3D. Oh, we developed also one model for leakage inductances in the end winding, but that was all detailed calculation one. Yes.
Yeah, that's maybe also a point of my question. Yeah, the leakage inductance in the coil end. Yeah.
Yes, yes, but no efficiency map 3D yet.
Okay.
Maybe we need a little bit bigger pieces. Or maybe you need to use your cluster.
Yeah, sure.
Yes, this is possible as well.
Yes, we have done it. Also, that was another point. So we have also, as well as the tool, of course, we have several times used also JMAG cluster or PowerSys cluster. I always mix these two companies, but JSOL and PowerSys. But we have used also your cluster. It has been quite successful experience. But also, as well as that, your consulting basically services, which has always been helpful for us, especially provided by Eve and arranged by Quentin.
Thank you, Shafiq. Yes, indeed, we at Powersis, we do not only provide the software and the technical support, we can also help you to run calculation or to do any type of calculation you are not able to do by yourself. So, and this is what also a part of our collaboration with ABB. Okay. So, Stefan, Shafiq, is there anything else you would like to say or?
From my side, I would like to again thank PowerSys and also JSOL for providing all this support during the last year. I have been a JMAG user from 2009, more or less, from my PhD time. And from that time, I got in touch with Eve directly. And there were some other colleagues who left and came, but Eve has always been there for the support and also Corentin for all doing this arrangement that all the interfaces now are working pretty fine. That's thanks to your support. And also we had, of course, always close collaboration with JSOL as well. We had a very helpful meeting in Turkey in Switzerland together with JSOL and Takashi, Mr. Takashi. And it was also very helpful. So we have got always very good support from both JSOL and PowerSys, and we really appreciate it. We hope we can continue this collaboration closer in future.
Thank you for this very nice feedback.
Thank you, Shafiq. Thank you.
And thank you for your nice presentation today. I think it was very interesting. So just a last word on my side. I will just share my screen shortly to share with you last information from the PowerSys team. So you should be able to see my screen now. Eve, can you? Oh.
Yes.
Do you see the right?
No, the wrong screen.
So no, it's okay, right?
Yeah, now it's okay.
Okay, so just to let you know that we will schedule an interactive training program for JMAG that will take place online from November to January to November to 2020 to January next year, and will be composed by 9 modules. So for example, if you want to learn what we discussed today about loss evaluation or JMAG, there will be some module about that. So you can choose the module you want according to your needs and objectives. Or you can do the complete training program if you want, if you are a beginner and you want to get an advanced level of JMAG. So I will put the link of the registration on the chat panel of Zoom. Let me know if you want to know more about this training program, but I think it's a very good way to learn how to use JMAG and for any level, even if you are a beginner or if you already have some experience, but you want to get to know some advanced features. So this was the only thing I wanted to share. So Thank you again, everyone, for attending this session, and thank you to Shafik and Stefan for your very nice presentation.
Thank you very much,
you very
everyone, and
much.
also the time, and also Stefan for your time, and yeah, everyone. Thank you very much.
Thank
you.
you. Bye.
Bye
Bye
bye.
bye.
See you.